And good afternoon, everyone, and welcome. It's great to see so many of you joining us today, and thank you for taking the time to be part of this session. Today's webinar brings together three research presentations from the University of Auckland's Engineering for Natural Hazard Mitigation Research Center, highlighting some of the important work currently underway to better understand how structures perform during earthquakes and how we can improve their resilience and recovery. Over the next hour, we'll explore three different areas of research. First, we'll hear about the effectiveness of repair on damaged reinforced concrete components and what recent research tells us about how well repaired structures may perform in future seismic events. This presentation will be delivered by Alex Shegay. Next, we'll look at the collapse potential of unreinforced masonry structural components with insights from an extensive experimental testing program investigating how masonry walls behave under different earthquakes motions. This presentation will be given by Anastasios Ioannidis. And finally, we'll move to resilient mass timber structures with a full-scale experimental study of a two-story CLT building incorporating rocking wall systems and tension-based bracing designed to achieve performance beyond life safety. And this presentation will be delivered by Ashkan Hashmi. After all three presentations, we'll have a QA session, which will be facilitated by Jenny, who will guide the discussion and bring your questions to the speakers. With that, let's get started. And I'm pleased to hand over to our first speaker, Alex Shegay. Alex.
Yeah, thanks very much, Julio. Yeah, it's a great opportunity, so thanks for having me. And yeah, I am honored to be presenting to our best engineers in the country. So my name is Alex Shegay. I am a senior lecturer at the University of Auckland, and I want to talk about today a multi-year study that we did on looking into the effectiveness of repair on concrete components. And way back when the study started, what is it, 5 or 6 years ago now, I always showed this slide up on the screen. I was living in Japan at the time, so people were always shocked by this slide, but I think people in New Zealand are more or less used to these pictures here. And the point of the slide was to show that, we had a city, we had a severe earthquake, and we had about 4 or 5, severely damaged or collapsed buildings. But we ended up demolishing 60% of the city's building stock. And so there was a lot of complexity in how those decisions were made. Insurance played a huge role in it. But one sort of reason we chose to focus on was this uncertainty associated with repairing those particular buildings. So we undertook the study to better understand how repair affects damaged concrete components. And at the time, there wasn't much guidance out there. There's a little bit more now, but at the time, there was two sort of documents that we referenced that gave people ideas on how to account for repair in damaged components and perform analysis that way. But we thought we'd supplement this existing research with some new data. And I thought for today's presentation, instead of me diving into one specific research into depth, I thought it'd be a good opportunity to sort of present a spread of various research projects done within this program. So I'm going to focus on three in particular here: a full-scale test on the concrete building, component tests and performing full repair of those, and then partial repair of some concrete component tests too. And so the idea is to give you a taste of what we did in these studies, and then I'll be happy to provide you further resources if you're interested in the details. So starting with this full-scale experiments, the objective of this test was to investigate how system-level structural performance can be recovered following what we called simple repairs. Okay, so I'll emphasize the word simple because we didn't implement any proprietary techniques. We didn't retrofit the structure. We sort of did your run-of-the-mill epoxy injection, etc., which I'll talk about in a second. And these are the structural characteristics that we were focused on understanding. So we happened to have a damaged structure. We had damaged a four-story building. I think it was a quarter scale from memory. And we thought, why not repair it? Okay, and get another test out of it. So at the time, the structure had reached its basically ultimate capacity. The shear wall, which you can see up on the screen here, had crushing in its end region. The bars had buckled and basically lost most of its lateral capacity, while we had classical sort of hinging damage characteristics in the column hinges at the base of the columns and also in the ends of the beams. So characterized by spalling of concrete, but luckily no buckling. And so the way we repaired these specimens, these members, was for areas that had no spalling, so just cracks. We basically injected everything. Any crack that you can see that was sort of practically injectable, we pumped epoxy resin into them. For areas where we had minor spalling, we used polymer cement mortar to patch those areas almost as a aesthetic repair. For more severe spalling, where you could see the rebar, we patched that with epoxy mortar. And then for the wall, which basically failed, it had buckled rebar. So what we did is we removed the concrete area that was damaged. We cut out the buckled bars and we replaced them with new bars. So that's what it looked like after repair. I'll start with the top left-hand figure. So minor spalling in the base of the columns, patched with polymer cement. More severe spalling, exposing, reinforcing bar. We implemented epoxy mortar. So in both of these cases, no formwork is needed. You could just slap it on. And then for the severely damaged wall, we basically cut out bits of the wall with the damaged concrete until we had stuff with good purchase. We cut out the bars and spliced new ones using welding. And that basically went down to the foundation. And then this looks like a bit of a shoddy job, but we did put concrete into it. There was a little bit of honeycombing, which was patched up later, but this did require local formwork. So looking at the damage after the repairs, so we took the specimen through a series of excitations again, basically to the same level of drift as the original specimen. And here is the damage outcome. So in the columns that had sort of what we'd say severe spalling, exposing rebar, we couldn't see that spalling happening again. Because partially we think it's because of this material that we used, epoxy mortar, which had a bit more compressive strain capacity than concrete. In some cases, like in this beam here, the patched damaged area basically moved out, so maybe hinge relocation to an extent, and you got spalling in the original concrete a little bit away from the hinge. In some beams, we didn't see any spalling at all, so this was quite a severely spalled area, patched it with epoxy mortar, and it didn't spall again. And then for the wall, which is basically replaced with like-for-like components, the damage was basically identical. And basically the identical roof drifts, we had the same bit of concrete that blew out and the same rebar buckled. The splice was further up, so the splice remained undamaged, but the new rebar basically buckled. So if we look at the hysteresis results for this specimen, on the left we have sort of the hysteresis plot for various runs. And if I take the backbone of this left-hand figure and plot it on the right-hand figure in black, okay, so that's the backbone of the original specimen. And all the colors show the performance of the repaired structure. So the structure as a whole over multiple runs. And it's a bit of a messy plot, but maybe I'll just point some things out. You can see in this sort of initial stiffness area, the repaired specimen has lower stiffness than the original. That's to be expected. We can't recover all of our stiffness from epoxy injection. But as we get to about yield, so if we look at yield, sequence stiffness, we're basically back to where we started. And then furthermore, the repaired specimen just kept increasing in strength. Okay, so we got to about 115, was it 10%, 10 to 15% more strength than the original specimen, and the deformation capacity was basically unchanged. So they both experienced that wall failure at about 5% roof drift. Okay, that looked good. So then we thought, okay, we kind of got an understanding of what these repairs are can do at a system level, why don't we do the same for a member level? But this time, get a little more precise and try to quantify that recovery at the member level. Again, using simple techniques. Okay. So we took a number of wall specimens. This figure is more blurry than I'd like it to be. This is about 1.5 meters in height. Same for the beam specimen. It looks like a column, but this is a beam on its side. So it had no axial load. And they were basically extracted, the design was extracted from the full scale specimen and then just scaled, not the full scale, the shake table specimen, and then scaled up just a little bit bigger. And then subjected to static loading. The testing procedure was basically to load the original's members to either its yield points or to spalling, which is a little bit beyond yield. Then to repair those specimens using those simple repair techniques, and then to load again to failure. Okay. And here is an example of what some of those repairs look like. This picture on the left looks crazy and creeps me out with all the little tubes, but that's how epoxy injection is often done in Japan. So these little cartridges of epoxy, and it's sort of gravity fed overnight into the crack. So what we call this a full repair. So whatever you can see in your crack that you can see, seal it up and pump epoxy into it. The corners that spalled had epoxy resin mortar as previously, and same for the beam specimens. This is quite a severe case with severe spalling. Of course, we had to push that beam back to its 0% drifts and then patch it all up with epoxy mortar, and we did inject those cracks afterwards. So here I'm showing the performance of these specimens, particularly the wall at this stage, at 2% drift. So at 2% drift, this is the picture of the original wall's damaged state. The one below it is the wall that was repaired after it yielded. Okay, so basically identical damage patterns. And the one below that was the wall that was repaired after it spalled. Okay, so there's a bit of a difference there, right? So as we saw in the structure previously, the areas that were spalled initially repaired with epoxy mortar didn't spall at the same drift level. Here's the beam, basically the same. Okay, so at 1% drift, the original beam and the beam repaired at yield, excuse me, basically look identical. And the beam repaired at spalling looks a little messy because that's just the nature of the epoxy mortar. The damaged state was basically identical. And at 2% drift, the beam looked like this originally, repairing at yield, a little bit less spalling, but basically identical performance to the original specimen. And the beam repaired with epoxy mortar, again, didn't exhibit the same level of spalling as the original specimen. And again, we put that down to the fact that this mortar is a bit more flexible in compression and has a bit more strain capacity in compression. If we look at the hysteresis of these walls, and this is the wall specimen I'm showing. The black line shows the original specimen. Okay, so from kind of no damage tested to failure, and the red line shows the wall that was repaired at yield and retested. So basically identical performance here. On the right-hand side is the wall that was damaged to spalling and then repaired. And you can see basically, again, identical performance to the original specimen, other than the fact that the repaired specimen again had an increase in strength. For the beam specimens, basically the same pattern. Okay, so not much difference in the hysteresis between the original and the repaired. When you repair at a later damage state, your strength seems to increase. And what you can't really see here is the initial stiffness, of course, that decreased for the repaired specimens. But at yield, when we get down to yield, which is the squares here, we're basically getting the same performance of these members. And so the culmination of this study was this table here, which is basically us trying to guide engineers on how you could analyze a repaired structure. So here is a table that's organized by characteristics of initial stiffness, the yield stiffness, the strength, and damping of the member. and then you have the damage level to which it's damaged prior to repair. And then you have the member type, right? So you have the wall, the beam, and the column in the silent. Okay. The numbers here tell you how much out of 100% you recover from your sort of simple repair, right? So for example, a member that's a beam damaged to basically failure, damage level 5. I won't go into what these mean, but there are definitions. Damage level 5, with a simple repair, you will only get to about 60% of its original stiffness. You'll get to 70% of its secant stiffness, and you can get up to 20% more strength after that repair. Okay, we also looked at damping, but I won't go into that. And I would also note that these numbers were not just from the study I presented, uh, they were taken from a database of other repair studies we looked at, into as part of this bigger study. Okay, and finally, we looked into this idea of partial repair. And the objective for this study was to determine if even simpler repair can be achievable, or still achieve comparable structural performance. So the idea is, you don't have to inject every single crack like in this picture here, but what if you just focus on a specific area to try to reduce your cost, but still get your performance? So we call that partial repair. So this is the concept. We built 5 beams, again, look like columns on this side. The beams were loaded statically to induce a damage state, so maybe a heavy damage state with severe spalling and some moderate damage states with no spalling. The beams were repaired, so either a full repair, as previously you inject everything, you patch everything, or a partial repair. So in this repair, we only focused on the theoretical plastic hinge zone. Okay, so put your energy into that one sort of critical area and ignore all the damage in the rest of the specimen. And then we had the unrepaired sort of virgin specimen to compare. And then finally, after repair, we reloaded all of these specimens, this time using dynamic shaking, so shake table test. And that was just to capture some energy dissipation characteristics as well as to get a bit of a more realistic response of these beams. Here's a couple of pictures of that partial repair, again, focusing all energy into that plastic hinge zone only. Here is a backbone comparison. So this is a force versus drift plot of the 5 specimens. So the red line is the unrepaired specimen, which means we damaged the specimen and then we retested the specimen without doing anything. And of course, it has a very low stiffness and naturally a lower strength at a certain drift, right? Because it's still trying to reach that previous peak. You don't get any recovery, right? Because you haven't done anything. Whereas if you look at the full repairs, the green line, the purple line, the partial repair, which is the blue line, and the undamaged specimen, so this is sort of your new equivalent new specimen, they basically had more or less very similar performance. Okay, so I guess yeah, I should mention that initial stiffness does still drop. You don't get back to your undamaged specimen, the orange line. And interestingly, again, the strength of your repaired specimens increases a little bit above the undamaged specimen. But at the yield point, more or less, if this is kind of the yield region, you're basically back to where you started. And that was to show that, you could do less in your repair and still get a pretty good result. And then the person who did this work, they actually did a really rough comparison of costs by implementing a partial versus a full repair. And they said if you repair, if you focus just on your plastic hinge region, maybe you can get a cost saving of maybe like a 20% cost saving versus trying to inject every single thing you see. Okay, I think I'm coming up to time, so I'll just summarize here that our full repairs seem to recover about 115% of strength. We always got back to the same deformation capacity. We got 85% of yield secant stiffness, at least, and typically maybe 60 to 70% of initial stiffness of these specimens. So partial repair is promising. So we got pretty close to these numbers with less work. And the effective repair was verified at the system level. So that was the very first study I showed you. So this research involved a bunch of people and a bunch of organizations, which I'll acknowledge here. The studies are presented are mostly published, so you can refer to references here. I'm happy to share these in the future. And that's it. Thank you for your attention.
Thanks, Alex. We don't have any questions yet in the Q&A. Actually, now one has just popped up. Okay, so from Julian Rincon, thanks, Alex. Interesting partial repair concept. How did you determine the extent of the hinge region that you selected for repair?
Yeah, good question. So I think in the presentation I mentioned the theoretical plastic hinge. So that was our guide. So we used basically half the beam depth just to start us off. But what we actually ended up doing is looking at the curvature profile of the specimen after testing, and then sort of it was a bit of an approximate decision, right? There wasn't a hard line, but we'd say, okay, it looks like most of the curvature is concentrating on this height, which was more or less close to that initial assumption, and that's how we made a final decision of, okay, this is going to be our cutoff for that repair height.
Cool. Thank you. We'll move on to the next speaker, and hopefully we'll have a bit of time at the end to cover some of these extra questions. But thanks, Alex.
Thank you.
All right, thank you. First of all, thank you for the invitation. I'm really happy to present a project that I've been working on with some colleagues from Portugal and France. My name is Anastasios or Tassos Ioannidis, and I'm a lecturer at the University of Auckland. And today my presentation is titled The Collapse Potential of Unreinforced Masonry Structural Components. Before I continue, I would like to acknowledge the contribution of my co-workers and collaborators from both France and Portugal, and mainly the first two people who were our PhD students. They have now graduated, and I can just guide you to follow this link if you want to learn more and more actions and more research, apart from what I will present here. Now, regarding unreinforced masonry structures, you all know that are part of our build cultural or not heritage. However, they are vulnerable to earthquakes due to their low tensile strength, and their main collapse mechanism is either in plane or out of plane, with the out of plane being the most common. So we usually, when we want to seismic assess an unreinforced masonry structure or an unreinforced masonry component actually, or collapse mechanism, we use probabilistic treatment. And for that probabilistic treatment to be more reliable, we need to have experimentally driven limit states, drift or rotation limit states, and fragility curves. The collapse mechanisms of unreinforced masonry buildings are well documented in the literature from the 1999. The main collapse mechanisms are cantilever wall, which is the simplest and more common, the one-way bending or the vertical spanning strip wall, and then we go into a bit more complex mechanism, which is the two-way bending. And finally, we have the corner, which is a result of an in-plane and out-of-plane interaction. We will focus on the cantilever and vertical spanning strip wall. So the main parameters that affect their stability is, the overload and the boundary conditions. Especially for the vertical spanning strip, the boundary condition has to do with the wall diaphragm connection. We all know that even if it is anchored, that anchorage may not be functional after some time, and whether we assume that we have rigid or flexible diaphragm. So the objective of this study is first to investigate test repeatability. This was on the right-hand side, one of my night scrolls when I was in Guimarães. This is a wall built in 1318, and used to protect the people from the enemy. And if you have a closer look, you will realize that there is no mortar left. Okay, so that's why the dry joint configuration. But we all know here in New Zealand that what we say is strong break weak mortar. Okay, so we expect that mortar to fail first. We are interested on the hinge height, so it's where this intermediate hinge will happen during an earthquake. By the way, this wall behaves as a cantilever wall, but we will investigate both of them, both a vertical spanning strip wall and a cantilever wall. We have also another objective is to construct, build, if you like, experimental overturning plots or spectra under both pulses and recorded earthquakes, which are really simple plots that provides the seismic response with respect to the signal and structural characteristics, drift or rotation limit states and fragility curves. And I have two more actions that unfortunately I will not be able to present here. It's the effect on the stability, on the seismic stability of the boundary conditions, which is really important, and the energy dissipation throughout the time history. However, feel free to follow these references for more details. Now, the shaking table testing campaign, regarding the cantilever wall, as I said, we have to scale down the structure. We didn't have the capacity of the shake table to do full scale test. However, we adopted three different aspect ratios. We used a DAC acquisition system consisted of 4 cameras, and we wanted to test repeatability, experimental overturning plots. We also did these two, but I will not present you, unfortunately, for lack of time. So first thing is test repeatability. This has been sent for, it's an issue that we're facing when we're doing a test. How repeatable is a test? So what we have here is we adopted a single specimen under a single recorded ground motion, and we run the test 5 times. So 5 times, and we chase the scale factor of the accelerogram. And this is the results. So for the high and very strong earthquake that we have collapse, you see that we have repeatability. Someone might argue that even for a weak earthquake, we can have repeatability. But definitely for the other cases, we cannot have, and we don't have test repeatability. And now the problem becomes even worse when we assume 3 different specimens of the same aspect ratio, but different specimens. Okay, what it changes in reality here is that we increase the uncertainty in terms of the interface, the contact interface. Okay, under a single single ground motion, 15 repetitions, and you will realize how unpredictable is the response, or if you like, how repeatable is the response. And we concluded some more than 100 tests for that, but you will see the main outcome out of this series of tests. Now, we continue by subjecting cantilever walls into pulse ground motions, and we build these they look nice, if I'm honest with you, this experimental overturning plots or spectrum, which is simple plots that provide the demand, so it's the response. Different colors, I will explain a bit later on what are the different colors are. So on the y-axis, we usually have the ground motion acceleration, the peak ground acceleration, for instance, normalized with a measure of the aspect ratio of the wall. So this is dimensionless. And the x-axis is also dimensionless, that we use the ground motion frequency over a measure of size of the wall. And the interesting part here is that threshold keep in mind, because we used pulses, that's why that threshold is so smooth. We can have the same threshold under recorded earthquakes, but with that threshold will not be that smooth. It will be more jagged. But what you need to know is that we have closed form expressions, mathematical expressions that describe those boundaries. Now, the interesting part here is that from between direction A and direction B, what we changed actually, it's the way is the direction of the earthquake, one way to think about it, which is the same if we rotate the cantilever wall 180 degrees with respect to the Z vertical axis. So what we have actually is that we capture very well that boundary here, which is collapse, direct collapse here, and collapse after a single impact here. And we fail at this shift. We have this shift when we change the direction, while we have that shift here, and we capture almost perfectly that boundary threshold there. And the reason for that is simple. After we did the post-processing, is that the interface has a slight asymmetry, so it has a slight slope, very, very slight, in the order of 0 point something %. So that makes that difference in the dynamic response. Now, regarding the vertical spanning strip wall, the experimental setup was slightly more complicated as expected. However, we did our best in order to capture the dynamic response and to have different aspect ratios. So 2 different aspect ratios, 13 and 15, H over B. H is the total height and B is the width of the wall, and different overload conditions. We use the same DAC system, of course, and we derive the overturning plots and fragility curves, limit states as well. Energy dissipation and boundary effects of boundary conditions, we did it, but I will not present you in this presentation. For the boundary conditions, it's really important. It makes a difference because we also investigated, but I will not present you here. So we assume that we have a rigid diaphragm, so the wall can move only up and down, not left and right. So we don't have like a spring-like diaphragm. And for the overload, we use this kind of springs to apply pre-compression to the wall. Now, keep in mind that we had some certain capacity limitations of the shake table, so that's why it's a smaller scale specimen. And these would, the amount of pre-compression was in order to allow us to force the wall into collapse. The first part that we wanted to investigate is the hinge height. You all know from C8 that we consider the hinge height to be 50% of the total height. In reality, and this time show you the results of a single time history response of a single test. And with these dots is where, from the DAC, of course, after post-processing, is where we have the hinge height. Now, the hinge height, as you can see here, is dominated by around 0.55 to 0.65. At the same time, we are allowed to have multiple openings only because the dry joint, okay? So here that we have lower rotation, so the darker the color, the highest the drift or the highest rotation. However, the lighter the color, the lowest the drift or rotation. So someone might argue, and it's correct, that at this stage, for low rotations, if we have mortar, we will not have these openings here, okay? But this is dominated by an opening at 0.55 to 0.65. And we continue by applying shake pulses on this wall here. And we build the same or similar overturning plot, okay? Ground motion acceleration over something related to aspect ratio, frequency over size. And again, we have a nice boundary, if you like. Okay, this is collapse and this is the safe rocking response. And we have a nice boundary distinction between the response modes. The closed form is on question mark because we still do not have a mathematical expression that can capture that kind of boundary. Not yet, at least. We wanted to treat the problem from a probabilistic point of view, so we apply incremental dynamic analysis, both aspect ratios and different overload conditions. So we realize that, of course, increasing the overload, the stability of the wall increases. And this is somehow 190 Shegay table tests. And in order to go to a more probabilistic point of view, we use the stripe analysis and we fit a log normal cumulative distribution function using the maximum likelihood estimation proposed by Professor Baker. And I will show you only the results after adopting PGV as the most optimal intensity measure. Someone might argue it's not PGV, but for the collapse, it's PGV for a rocking structure or an unreinforced masonry part. And we find out based on the likelihood and the dispersion, we want the likelihood to be higher and the dispersion to be lower, 3 experimentally informed damage limit states. And if we draw the fragility curves, these are the tests, by the way, the mean value of each test for each stripe. We have the 3 fragility curves for the 3 drift limit states. On the x-axis, mainly we have PGV, but we like to normalize the axis, so in order to be in dimensionless terms. So to conclude, we conducted a bit more of a 500 Shegay table tests. However, I have to clarify that we lose the scale because it wasn't full scale. So we gain in the number of tests when we decrease the scale of the test of the specimen. Test repeatability, I will simply say that it's quite challenging and it needs to be carefully considered when we conduct an experimental campaign. The experimental overturning plots for a cantilever wall is in quite acceptable agreement with the closed form solutions. However, we don't have closed form solutions for the vertical spanning strip, so this was something new to us. The higher the overload, the more stable the vertical spanning strip, which is something which is intuitive. The hinge height was in the order of 0.55 to 0.65. And the drift limit states were developed after a probabilistic treatment of the rocking problem and defined 3 limit states, drift limit state, 0.15, 35, and 65. So that is for me. Thank you for your kind attention.
Thanks, Tassos. Quick question for you. Do you expect this work will likely result in updates to C8, or are there any recommendations you have in the interim for engineers in using C8?
Well, C8 was recently updated, so if I'm honest with you, I don't know whether it merits further updates. So let's see the new one. We have seen the new one, but hopefully sometime in the future, yes, why not? Not at this time now because it still has updated in 2025. So, but yes, that's the main point. That's the main idea. This work happened with another country in mind, and Portugal in particular, which is full of heritage structures made of limestone. But yes, definitely it can be applied in the New Zealand reality.
Great. Well, thank you. We'll pass now to our final speaker, Ashkan.
Great. Okay, first of all, thank you for CSOC for providing the opportunity, and hopefully we can carry on with more research updates to bring the research and practice closer. So I'm the last one. I'll try to be faster than Alex and Tassos to leave some time for questions and answers. So today I'm going to inform you about a research that was concluded last year about full-scale testing of a resilient mass timber structure. Research was a result of two PhD projects and several other undergrad and master research projects over a period of 4.5 years. So what you see is a result of that. To give you a bit of context is why do we use mass timber? So we intend to decrease construction time, weight, and then variability through using mass timber elements. Also, the carbon footprint, we want to bring it down. And at the same time, New Zealand has one of the best structural wood in the world, and it's sort of a domestic industry, mass timber industry. So we intend to use that. However, we are a seismic country, and when conventional timber structures undergo earthquake, this will happen to the connections. Basically, conventionally, timber connections are made of brackets and fasteners like nails, screws, and bolts. And what happens during lateral cyclic loading is that the system presents pinching, which means subsequent decreasing the stiffness of the system until it's actually zero stiffness. So we have pull out of the fasteners, yielding of the brackets, which makes the system actually a one-off if there is a major earthquake. And there is research showing that if a conventional timber structure goes for close to 4 full cycles of its drift capacity, actually the stiffness will be close to zero afterwards. Also research had a sort of a focus on wall-to-floor connections, which I'll describe later on. Which, as you can see here, these are the typical wall-to-floor connections used in conventional mass timber structures. And as you can see, there is, as the structure moves laterally, there is a major issue in terms of displacement compatibility that causes this sort of damage to the structure. And yeah, more photos from different failure modes of connections, but actually all of them either splitting or yielding of the fastener result in the same thing, which means losing the permanently losing the stiffness of the structure. Now, what we intended to do is to replace all the connections in a sort of a structural system with connections that are either no damage or repairable. So to come up with a resilient structural system in 3 dimensions and full scale. We have been doing incremental research on that for the last decade, but last year we managed to have a sort of a system level testing to demonstrate the performance. Yeah, so, and conventional structural systems demonstrate the pinching behavior. Also, we do have systems that have been years ago developed at the University of Canterbury, and now it's being followed up by researchers in the United States, post-tension systems for timber structures. We wanted to sort of move away from that as well, since the potential issue that post-tensioning in timber could have, or some cost issues. So my point is, for our research, we have not considered any post-tensioning in timber. So what we had was a timber wall system that we were using, sort of similar to a couple wall system. We were using resilient hold downs at the base, and also as an active link between the walls, a conventional friction damper. So the motivation was to have a resilient base design, to avoid the loss of post-tensioning force, and also complexity on site and costs associated with implementing a post-tension system, to demonstrate it in full scale, and to inspect and investigate the behavior of every and all connections involved, and sort of address any uncertainties about the performance. How did we design the specimen? That was a long journey, but we sort of ended up using a methodology similar to P695, FEMA P695, which is about design and testing of sort of new structural systems. So what we adopted was similar to this, but it was within New Zealand context. This is the sort of the test specimen that we had, 6 meter wide and 6 meters tall. And well, we say full scale because we try to maintain the width and height of an actual building, but obviously we couldn't do a fully like a full apartment building. So that was the biggest we could go based on the constraints that we had in the University of Auckland laboratory. So this shows the type of connections we used. As mentioned, self-centering hold downs at the base, low damage shear keys at the base, and at the first two levels, friction dampers in between the walls to encourage the coupling actions. All the other connections also made of sort of repairable, flexible connections that I'll explain in detail. Yeah, so here you can see sort of examples of the connections used. All the connections were sort of designed to encourage prefabrication because, as we know, on-site installations of thousands of timber fasteners could be a challenge. So therefore, we came up with concepts adopted mostly from international practices from Europe and North America to make sure that the system remains economical and mostly prefabricated. And here you can see the friction damper implemented in between the walls. So for a taller structure, what we realize is that you wouldn't need to have these friction dampers as coupling to provide coupling action across the height. It could be actually at every other story or every 3 stories. That will be sufficient for a building designed in New Zealand environment. So all of the energy dissipation devices used for testing were component tests before implementing and installing on the structure. So this shows the performance of the friction damper used between the walls. Also at the base, we used self-centering hold downs that was sort of developed at the University of Auckland years ago and have been implemented in practice and research for years, but this was the first time it was tested on a full-scale timber structure. And you can see a sort of the pin assembly sort of design for the column to make sure it can rotate to about the target drift without significant damage to the timber or any other component. And that also shows the component testing of the friction spring dampers used as self-centering one. So as I mentioned, all devices went through a pre-qualification test before being installed on the main specimen. So I'm going to talk about shear keys a bit more details, just in a few more slides. One thing to note is that one important finding from this research was when you're using CLT walls, you better reinforce the CLT at the corners where it intends to rock or it bears on a shear key. You need that sort of similar to a reinforced concrete system. You would need to have the reinforcement to avoid the cracks and brittle failure of timber. So that's something that we found and we implemented. That was a major finding. So for the testing, we used unidirectional testing in both direction X and Y, and also bidirectional testing based on FEMA 461. For unidirectional testing, the structure was pushed to about 4.1% drift, but this level was not governed by the drift limitation of the structure, but was more like limitations of the lab. And also for bidirectional testing, pushed to 2.5% in the wall direction, 1.5% in the transverse direction where we had X bracing system. These are some results from the in-plane tests. As you can see, where you only have the hold-down connections, you would have a self-centering more or less system. But when you add the sort of the coupling damper, it's semi-self-centering, which this sort of is tunable. You can just tune the capacity of this damper versus the capacity of the wall hold downs to come up with the ideal system you have, because self-centering is not always a must. It's a nice to have for many cases. So the system in that sense is tunable to achieve the objectives. Also for out of plane testing, we had a X self-centering X bracing system, whereas self-centering joints were used in series with the reed bar system. And that presented a fully self-centering behavior as well. So here I'm showing you a video, very quick one of the in-plane test. Not very exciting, but the achievement was everything worked as expected, and we didn't observe any damage anywhere in none of the connections. And also here is the bidirectional test results. If you look at the X bracing system, you can see that it drops in compression. And a closer view of how the coupling damper behaves. I hope it's visible. Video is a bit slow. Okay, maybe I'll just move on. On my screen, it's not great. And then the hold downs. So you could see the shear keys here. I'm going to talk about them in a bit. Yeah. So in terms of wall to floor interaction, so to give you a bit of context, traditionally there are two types of wall to floor connections. Conventional design, they're rigidly connected to each other using fasteners for mass timber systems. And when the system laterally moves, the wall wants to go up, the beam doesn't want to, or the floor doesn't want to go up, and there'll be damage here. For this structure, we try to decouple them in a way that the wall remains a lateral load resisting system and the gravity is transferred through columns. We use two different types of shear key, multi bolted connections used at the base and also at the wall-to-floor connections, which actually work really well and sort of demonstrated that through simple bolted connections, you can achieve what you cannot achieve with conventional fasteners. The difference was the holes for the shear key. There were slotted holes, but a slightly profiled to a heart shape. So the wall can so the system is encouraged to have a rocking mechanism. This video shows how the shear keys behave. And then again, further tests showed that there is no actually resistance coming from the shear key, and the system performed perfectly well under that. And here are the results of the sort of a displacement, vertical displacement at the base, first level and the third level. You can see they're fully compatible, which means there was no jamming in the shear key and there was no odd behavior observed from the wall-to-floor interaction. And a post-test inspection showed that all the holes for the bolted connections remains intact almost. And same for other connections. And also, we've tested a single dowel shear key because that we wanted to compare this with our multi-bolted shear key. And they perform roughly similarly, and this is from the roof. The single pin also provides the required displacement compatibility, but at the same time, it ends up being a more expensive option. So we had this in place for the case that the multi-bolt connection doesn't work or doesn't behave the way expected, so we can have an option B, but both perform well. Thank you. There has been a lot of publications from this test and also an extended video available on the Auckland Structural Group YouTube channel, which you can refer or you can just contact me if you need more information. I think the main finding was we managed to come up with a system in mass timber that is low damage, that has high ductility, and that has low overstring factor. So essentially an economical, resilient solution for mass timber buildings. Thank you very much.
Thank you, Ashkan. We have a question. How would you compare this shear wall solution with active link mechanisms between the walls versus a solution with just proprietary dampers at each end of the wall base?
Yeah, so it gives, so when you add the damper between the walls, you turn it into a couple wall system. So you get a lot more overturning moment capacity. So in general, it makes it more economical.
Okay. One more question. The dampers and the hinges that you use, are they proprietary systems or is that sort of like a proof of concept at this stage?
The ones at the wall base are, but the ones between the walls, no, they're generic friction dampers.
Cool. That is, so that's all the questions we have, and we are 1 minute early, so finishing perfectly on time. Thank you so much to all of our speakers, and thanks to everyone who joined online. It's been a really interesting presentation, and we look forward to seeing everyone at the next webinar. Take care. Bye.